Hello, welcome to our broadcast. I'm here to teach you an introductory course in chemistry. My name is Dr. Bettina Heinz, and I'll give you a good foundation so you can follow any other chemistry class now in the future. So today's episode is going to be an introduction to chemistry as a science, because chemistry is a universal science. It connects everything practically. So it really will help you in many other fields, but also make you understand your environment much better. So let's begin with our exciting adventure, and we will cover the topics, what chemistry is. You see here that it is the study of matter, its properties, its structures, and its changes. Then how matter and energy are related, how anything changing in the material sense also involves energy transactions and changes. The different branches of chemistry, and also how chemistry is practiced throughout the world. Many cultures practice chemistry, but they did not always have a written record, nor did they want to. Often it was secret knowledge passed on from generation to generation. But we are now in the Western type of chemistry course where we document everything. So the branches of chemistry, relation to other physical and biological sciences, the scientific method, as we like to say, which is not always as strictly followed as it would like to be, hypotheses, theory, law, principle, rule, models, etc. Non-orthodox methods like serendipity playing a role, curiosity, intuition, and how ideas set paradigms and sometimes even dogmas that lead to controversy. So the whole shebang is part of this field, especially when science is involved. It's always in flux. Now, the chemistry that we practice relies heavily on glassware. So you need the vesicles to undergo chemical reactions, to watch the chemical changes in the flask, and so forth and so on. Although we could say modern biotechnology now relies on a special type of plastic, which is called PETE for short. Polyethylene terephthalic acid ester, I think it is. Here we can go back centuries and millennia to ancient Egypt, where chemistry was practiced to quite a degree. There's probably a lot of technology that has been lost to us. On the right we have Greek depictions of glassware that were used for Greek chemistry, so to speak. The name chemistry comes from an Arabic word meaning or sounding related to alchemy, alchemia. So the word is an Arabic word. The Arabs and the Persians practiced a lot of chemistry and developed a lot of the glassware. I want to point out to you the top right picture where a retort is shown. You see I have one here in my hand, and this is not used anymore much, but we still had it in our collection in our college. It's just a little modified. It has a little opening here, so we can add the chemicals through this opening and close it with a certain stopper. So this is a primitive form of distillation for distillation purposes. And on the left we have set up from India in ovens. So we have old illustrations that tell us that chemistry has been carried out throughout the world, also going very far back into historical times. Here's a nice little illustration about Chinese mining metals in the mountains. And here we have already an alchemistic depiction of a certain chemical setup. It always deals with certain processes, and these processes were just as important as the chemicals themselves. So the process is the one that was more considered than in our present day. Here we have a lab in the 18th century Europe, very nice and spacious. I wouldn't mind having a lab like that to work in, with some modern equipment, of course. And here we have one also with helpers and assistants working in the lab. And the glassware is already very similar to modern times. Here's a joke. So many interesting lectures were given in England in the 19th century by Sir Humphrey Davy, who did a lot of experimentation that interested the public. So people came there on a nice Friday or Saturday evening to be entertained with their wives in the crinoline skirts and so forth. So this is sort of a joke about Napoleon. Here's a wonderful lab that reminds me of my own studying times in organic chemistry. It's a big hall in Gießen, a 19th century laboratory where everybody stands around and is doing their experiments and talking and chatting and drinking, and all this thing is going on at the same time. You see here also a lab assistant, and the people with the top hats are the PhD candidates. And here we have the other side of the lab. Now this whole thing is a museum, so it can be visited. And here we have a relatively modern lab, circa in the 1900s. This picture shows the chemist Baekeland, a Belgian person who invented a very important type of plastic or phenolic resin, which was called Bakelite. So Bakelite was used for the old telephones, the radios, and also for jewelry, and has a great value for collectors. Now, as I was telling you, we have chemistry all over the world. It's not always practiced with glassware. You see here in the Amazon regions, the Amazon people, isolated many interesting chemicals out of plant material. For instance, curare. This is one of the molecular types, an organic alkaloid, and the name is D-dextrorotatory tubocurarin chloride. So this was isolated from the plants, and the materials the Native Americans of South America used were folded leaves as funnels, and of course wooden containers derived from the forest as a type of beaker. So they were very ingenious in isolating the chemicals out of plant material to use as poison arrow potions, as we see here in the picture. And this curare is a neurotoxin that somehow does not affect the heart, so it's now used also in the medical surgery environment for operations. And what is also interesting, that the animals that are poisoned with curare will not harm the person eating the flesh, because in the digestive tract the poison has no effect, since it is a neurotoxin. Also in Africa, Asia, and so forth, chemistry has been practiced. The Africans developed a very interesting type of oven already millennia before our counting time. So it's about 1300 BC, where they developed certain ovens that produced a very good form of iron that they could forge into various devices like weapons, household items, statues, art pieces, sculptures, etc. So they used charcoal. The oven was sort of submerged in the ground. It was had convection of preheated air that helped the combustion along, because you needed high temperatures. So they could reduce the iron ores to elementary iron. We also have in ancient China, or it's actually already in AD, about the first millennium AD, in the Tang dynasty, fireworks were discovered. However, not for warring purposes, but for displays, for celebrations during New Year's times, and also to get rid of evil spirits. and they're still used today when people move into a new house. They first treat it with fireworks. And also to scare the enemies. It is believed that Marco Polo brought the technology back to Europe. Now, chemistry as a science, what is it? It is the study of matter and its changes, and the accompanying energy changes. For instance, here we have the shorthand depiction of a chemical change. We have methane treated with oxygen, or it will naturally react with oxygen if you activate the gas with a spark or a light or a match. Then it will combust to produce the oxidation products that are carbon dioxide and water in the final stages, which we call complete combustion. And it produces a lot of energy that we can utilize for heating purposes and for other chemical changes that we might want to carry out that require heating. Because with heat, everything is accelerated. The reactions are accelerated. So here we see the molecular types of the substances that we are using. So you see chemistry also is interested in the structural units of these substances that make up matter, like a methane molecule with 2 oxygen molecules, make a carbon dioxide molecule and 2 water molecules. Now this is a relatively simple reaction, but we also have in a more complex form a similar type of combustion or molecular change. For instance, carbon dioxide and water, with the help of light, in the leaves that contain chlorophyll as a catalyst, which is, strictly speaking, a very complex reaction. But overall, the net result is that we make sugars, carbohydrates. And oxygen is given off as a side product, which can be very valuable for the other forms of life that we call the animals. So the animals, by way of respiration, absorb or inhale oxygen, and through their metabolism, they give off carbon dioxide. So we have the reverse reaction to the top, which is sugar, carbohydrate. In this case, it would be glucose, plus oxygen, goes back into water and CO2. So this reaction, in one way, is utilized by the plants, and the other way, utilized by the animals. So we have a cycle of reactions in nature. So it's a cosmic thing if we suspect life in the universe, of course. Now let's look at chemistry as a natural science and how it is related to other sciences. It is a study of nature, and it, of course, involves a lot of mathematical background information because nature works in a mathematical way. So these are the scientists connected to these natural sciences, but we divide them essentially into the physical and the biological sciences. So the study of matter and energy of non-living materials and phenomena, in contrast to the study of matter of living materials, so to speak. So here we see the different sciences. We have physics, chemistry, astronomy, cosmology, geology, meteorology, etc. In biology, we have all the related sciences for the biological field. And the chemistry we divide up into general chemistry, organic, inorganic, analytical, etc. And we also have hybrids like biophysics, biochemistry, bioorganic chemistry, astrochemistry, and so on. And now we shall look at the scientific method. Now, the background information that we learn in our schools, colleges, and universities is actually there to help us if we want to become scientific researchers. Now, in the old days, people were just interested and observed their surroundings and then played around at home with their experimentation. Today, it's a little bit more structured, but still, we get a good idea, we follow it up, and do some background research, then set up a research hypothesis, a master plan for going about doing this research. Then we will do it in actuality in the laboratory. And then hopefully we get some results. The results might not coincide with what ideas we originally had in mind, but it might be still worthwhile to publish. And when you're lucky, you might even get the Nobel Prize if your research is worthy enough. Now, in chemistry as well as in other science, we have a lot of theories. Theories are pretty well established, but they're not 100% established. So if somebody comes up with a better theory, the old one has to be thrown out. Laws are really very established. It has been shown that laws will always be repeatable in its or their phenomena, like the law of gravity or gravitational force, the law of conservation of mass, for instance. Then we have a lot of rules and principles that are minor truths, or they're not so expansive on a grand scale, like Avogadro's principle, Dulong-Petit rule, Archimedes' principle, etc. We also have outdated or dismissed theories that might come back one of these days. You never know, but right now Haeckel, Lamarck, and the old phlogiston theory are no more in use. I would like to now show you a little video, lab video, that describes how carbon dioxide, as in its solid form, reacts with water to make really fun reactions that we've all more or less heard about or have seen on a stage or so. So let's see a video. Carbon dioxide and ice. Excuse me, carbon dioxide, dry ice, and water. Let's see that spectacle. Let's have some fun. Hi. Today we're going to do a little fun stuff. It's going to be party time. It is a little demo dealing with dry ice, which is solid carbon dioxide. It's an interesting ice. It's not like water ice. You can't liquefy it with increased pressure. It has a normal phase diagram, not like water, which is unusual. So it's really dry. And I want to show you in how we transport these cold materials, like dry ice, liquid nitrogen, and so forth, liquid air. So this is a Dewar container, sort of like a thermos bottle, spelled D-E-W-A-R. And here's a little piece. I have my gloves on, so if I use my bare hands, it would stick to my hands, to my fingers. Now, people who deal a lot with this are pretty much immune. They have lots of calluses on their hands, and they use their bare hands. I'm going to make a little smaller piece. So I use a hammer and wrap it with some material and pound it. Okay, I have some small pieces, and then I'm just going to throw these into some flask. And you see the violent bubbling. Now I can act like a mad scientist, like you've seen in the movies enough. And these solutions here are nothing mysterious. They're just food color water solutions. And here we have a big measuring graduated cylinder, so you can see really how the bubbles form in a violent fashion. Dry ice dissolves in the water and forms then carbonic acid. It's an acidic anhydride, CO2. By itself, it sublimates or sublimes, goes directly into the vapor phase. It skips the liquid phase completely. At normal pressure, like 1 atmosphere pressure, we will never reach the liquid phase. Although, if you lower the pressure sufficiently enough, you can reach what we call the triple point of carbon dioxide, and below that, you also have an area where you find liquid carbon dioxide, but not here on Earth with 1 atmosphere pressure. So we are way above the triple point, so the ice, the solid, goes directly into the vapor phase. We call this process sublimation. So no liquefaction, no melting, so to speak. And if you listen to the bubbles, you have some kind of music in your ears. And notice how the vapors sort of crawl down the side of the container. That's what makes this always so attractive, and that's what people look forward to when they have wild parties. See how this dry ice spins around? See, that would be nice to get a close-up of it. See what the others are doing? Yep. They use dry ice to make ice cream. So wherever you get ice cream materials, you can buy dry ice. It's $1 a pound. Anybody can buy it. But you have to wrap it up securely, and it doesn't last that long because of this sublimation. Well, welcome back again, and I hope you enjoyed that little demonstration. And this is a thing that you can do at your home. It's nothing dangerous, dry ice. You can buy at any ice cream provider or ice cream technology shop. And you can also buy the food colors, so you can have some nice party time. But now let's get a little serious and look at the theoretical background to all this. You have already heard some of it. We don't want to get too technical here right in the first episode, but I think it's always nice to know the background theory behind everything, because it makes things more complete that way. So dry ice and water, why do they do this interesting reaction? Well, it's no real chemical reaction, of course, but we found out that only water gives the best results. Other liquids do this thing too, but not to such a degree. It's not as spectacular as we would like to have it. But water is really the best combination with dry ice. Now, we have learned that carbon dioxide as a solid has a very interesting property, and that's that it sublimes or sublimates. That means it goes from solid phase directly into the vapor or gas phase. This is because of its particular phase diagram, which we can see here in our first view graph. And this is the PT diagram, as we call it, pressure temperature relationship diagram. It's like a map where you can see where is a chemical in its solid state, liquid or gaseous state. At the borderlines here, both states are at equilibrium, but we also have one point here in which all three states are in equilibrium, the solid, liquid and gas. This is what we call the triple point. Notice that the triple point is above the normal pressure that we experience here on Earth as human beings and with all our relations, the other animals, the other creatures. So we are all geared, we're all developed according to this 1 atmosphere pressure that we have in our environment. Now water has its triple point lower, so that means water can exist in its 3 phases in our experience. But carbon dioxide only liquefies at very high pressures. So you see here the liquid range or the liquid territory is beyond our bounds. So that means carbon dioxide sublimes. And that is the whole issue of our phenomenon, the fogging effect when dry ice is put into water. Why do we call it dry ice? Well, for that reason that the liquid is totally absent. The carbon dioxide liquid form is totally absent. So that means dry ice is really dry on the surface. So nothing gliding, nothing smooth like water ice, which is always a little slippery in our hands because of the liquid water that is on its surface. So the dry ice is therefore also dangerous to handle because it can cause burns, not real heat burns, but cold burns to our hands, because there's not this protective layer of liquid between our hand and the dry ice. Now, if we put the dry ice in water, it starts bubbling violently. And some people think, oh yeah, the water is boiling. But it's not boiling. It's just because of the gas molecules coming out of in their solid environment, going into the vapor phase, where they really want to be at this temperature, at the room temperature, for instance. So they get out of the liquid environment and bubble to the top, just like carbonated water or champagne would do, the carbon dioxide that isn't dissolved under pressure into these scenarios. But here we are going directly from the solid into the gas. So the gas molecules are rushing up to the surface, just like divers that want to get back to the surface as fast as possible. And they drag the water molecules, the water with them to the surface, and that gives that bubbling effect. And also the mist that you produce with carbon dioxide evolution here, that because of the violent escape, water is dragged with the carbon dioxide gas molecules into the atmosphere, so to speak, and this gives the fogging effect. It's the water that does the fogging, the mistiness. And this effect is used a lot for theaters, for movie businesses and concerts. You've seen it many times. So I hope this gets your attention going. We are going to have a great time here with chemistry. It is really the universal science that connects us to everything else in our environment. So bear with me and let's go on this adventure. See you next time. Goodbye.